Hello, um, my name is Nagihan, and today I'm going to talk about effect of process parameters on final geometry and quality of final product in hot tube spinning process. So this is my outline. Okay. So feeling like a family right now. So small here. Okay. First of all, what is spinning process? Spinning process is one of the oldest metal forming processes. When I say like one of the oldest, people usually visualize these kind of stuff, but actually I did like quick research, and then I saw like it can be traced back 4th century in ancient Egypt. You can see the two guys over here, and then like trying to do some ancient lathe over there. So when we are like talking about like conventional spinning, we have like a circular blank sheet metal, and we have forming tools, and at the end of the process we're going to have like more or less this kind of shape as a final product. But in this research, we're gonna have like tube spinning. So we have like tubular preform, and we're gonna have like rotationally axisymmetric and seamless product at the end of the process. Tube spinning process, like hot tube spinning process, actually preferred lately because we have a huge amount of plastic deformation, yet we have like relatively lower forces, but it might be complicated because there are like lots of deformation ways at the same time in the deformation zone, like shearing, thickening, thinning, compressing, and bending as well. So it might be get like even more complicated if we think about like calculate the forces manually, stress wise. So, and before I proceed with the objective of this research, I have to clarify something. This is not block forming process, because in the literature, specifically like in older articles, tube spinning is used flow forming synonymously, but actually it is not in flow form. We have mandrel and we insert preform on it, and then there are some rollers and shape the tubular preform. But here in tube spinning, here, this is our process. In tube spinning, we don't have any mandrel. We have just tubular preform and rotating, not moving in that direction, nothing. So objective of this research is to predict the effect of the temperature, reduction ratio, and roller geometry on the quality of the process using like finite element method with the help of commercial software called Forge. We use Forge here. And the methodology, we have like 2 different temperatures, 3 different reduction ratios, and 2 different roller geometries to see the effect of the parameters. And all of them make like 12 different combinations, of course. And we were like they were like simulated in Forge environment, and then got the results. So in our cat design, we have 2 rollers over here, and then like 1 preform and 1 headstock. Sorry, and as like rollers, we have 2 different tip radius. We changed only the tip radius over there. We didn't make any change with the what they call attack angle, let's say. And for rollers, we have like, actually, I wrote here like 2 degrees of freedom, but actually we have 3 because they are also rotating around their axis, which is that axis, and then they are moving in through that axis, and they are also compressing the preform here. You're moving in that way, and they're like just rotating freely. And then like when it comes to preform has only 1 degree of freedom, which is like moving along the z-axis. So you can see the like coordinate system here. What else can I say about the methodology of rollers? Nothing. So let's go with the preform. Okay. Preform material is like 42 chromium molybdenum 4, which is like alloy steel. I think it's well known. You can check the like if you would like to values of the yield strength, and then like we use like Hansen-Spitzer law as a hardening law, because we are dealing with elevated temperature here. So, and it considers like temperature, strain, and strain rates in this formula. So we chose this law. As a perform geometry, actually we have like roughly some geometry in our mind, but we have to comply with the standard. So we use like normal 20. Sorry for my bad German accent. If there is anyone coming from Germany, I can't. But okay, please accept my apologies. So for seamless carbon steel pipes and tubes, there's like a standard, and we chose from there and to fit the geometry in our mind. So this is the dimensions, not that much important. So when it comes to results, actually you can see here like process forces. This is an auxiliary result. It's not our main purpose actually, but it's always good to have like some idea regarding the forces. So I'm gonna explain fast. It's not that much has big influence. So temperature has an influence, like significant influence on force, process forces. When I say process forces, actually I mean like force in the direction of y-axis. Okay. So it has like significant influence on process force. You can see over the on the graph, the forces getting like decreases almost more than half, while roller geometry has almost no effects. Process force reduction ratio affects the process force in the y direction by 15 to 30%. So, okay. So this research like aims to have some idea regarding the effect of process parameters on quality of the process. So what is the quality of the process? When I say quality of the process, actually I mean like, okay, I have like a tubular preform, and then I have rollers, and then like rollers are moving, right? And then they are like drawing some arc shape. So what do I expect? I expect like exactly same outer surface with the path of the roller. So if they're like fitting each other, of course it's not going to be exactly same, but if they fit each other, then I can say like, oh, okay, the quality of my process, it's not that bad. But if there's like a really huge amount of distance between the path and the final geometry outside of the outer surface of my geometry final product, then I can say like, okay, it's not that much good process for me. I mean, this is what I am thinking when I say quality of the process. So how can I measure this? I can measure this with the wall thickness, like the effects of the parameters on the wall thickness. So let's look at the temperature. So temperature effect on wall thickness. You can see F1 actually represents the 15 mm tip radius forming roller, and the F2 the larger one. So you can see here like thickening, it increases when the temperature decreases over there. And then like in the case of F2, the other like the larger radius tip, except this one, it is like, actually it doesn't exhibit like similar behavior as F1, because like here, of course, we can say in the same orientation, the wall thickness like going in the same orientation, but there is no such similarity. Actually, I cannot say. Okay, I just realized. Okay, whatever. And then like let's move with the reduction ratio effect, the influence of reduction ratio on wall thickness. So thickening, at least 3 out of 4 is getting increasing or in the greatest value, where the reduction ratio was the highest value. So it's actually expected. That's what I was saying, actually, what I was trying to say when I was talking about the quality of the process. This is my roller path, and this is my outer contour of the formed part. So you can see like there's difference here. So, and this is the deviation as well. So I can say like it's 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 not like high quality process. And I can say like reduction ratio, when the reduction ratio is increasing, the deviation will also increase in one pass, That means like, what should I understand from this? If I would like to decrease the deviation, so if I would like to decrease this gap, then maybe I can use like multiple steps to form my preform. So maybe like if my reduction ratio has to be like 10 millimeter, then I can use two step 5 millimeter, or 6 millimeter, 4 millimeter. So in the second step, I don't have to use like higher reduction ratio. So roller geometry on wall thickness affects, we can see here tip of the tube. In the case of, again, like the S1, which is like smaller reduced tip, the thickness, thickening, increasing at the end of the here, and decreasing again, and increasing and decreasing again at some point. But when it comes to the higher, larger reduced tip, there is no such behavior. There's no such behavior. It's just like decreasing steadily. Okay, as a conclusion, when the temperature increases, the force in the y direction decreases almost half, by almost half. And the thickening, I was trying to say, when I say thickening, I was trying to say like at the end of the edge of tubular preform, getting at some point thickening. That's what I was trying to say actually. So it has the greatest value when the reduction ratio has the highest value as well, and I explained already shortly before. And reduction ratio and deviation, just short before, I also explained. So yeah, okay. Maybe use like larger forming zone radius. Maybe we can reduce the thickening end of the tube. Yeah. This is the conclusion, and that's it. Thank you.